addition uh, in probability and law of multiplication in probability. So this was the last thing that we have learned yesterday. Now we will be coming to the introduction to probability distributions. So binomial distribution and normal distribution. So now the question is actually, uh, there are different types of distributions within probability. Actually, one is called binomial distribution is type of discrete distribution, and normal distribution is type of continuous distribution in the probability. A binomial distribution is it models the probability of k successes and n independent trials with probability of p. Independent, now you understand what's independent events and what's dependent events. Independent events from this, these were dependent events, yeah. So whenever you were getting your sampling and getting a sample and then without replacement, you're proceeding to the next event. So the outcome of first event is affecting the outcome of the second event. So that's called dependent events. Independent events, that the outcome of first event is not affecting the outcome of second event. So it's actually sampling with replacement. So this is how you now have the understanding of what's independent event and what's dependent event. It actually, what is the distribution? It actually models, it visualizes actually the probability of k successes. For example, if we have, we want to know the probability of heads in a coin flip, and we want to know, for example, how many times we did that flip. For example, we did that flip 10 times, and from 10 times, 3 times it was head. So this is called, for example, whenever you're modeling such a distribution, such a probability, whenever you're modeling such a probability, that's called binomial distribution, because all of these independent events are actually dealt like a uh, discrete value. What is normal distribution? Normal distribution is continuous distribution where data is symmetrically distributed around the mean. So mean is here, it's very important. From SciPy stats, this is a library that we can, there is automatic functions, methods and libraries are existing within the Python. For example, if we have number of trials, 10 times we flip a coin, yeah? Probability of success for each flip is how much? Probability of success for each flip is 0.5. You know, whenever you're flipping a coin, either it's head, either it's not. So it's 50-50, yeah? And number of successes, it means from 10 times that we flip a coin, 5 times it got hits. So now calculate the probability. Very simple. This function provides you the probability calculation based on binomial distribution. So so what is k? K is actually the number of successes. For example, 5 times it was head. How many times we did this trial? We 10 times flip a coin. And what is the probability for each event? Each independent event? That's 0.5. Now, how much will be actually the probability of uh, the probability of exactly 5 successes in n trial is 0.2425, 25% almost. Almost 25% is the probability of this binomial probability here in this function. Now let's visualize this, for example. This is how we had 10 times, yeah? So this is 10 times we flip a coin, yeah? And this is how we prepare the range of 0 to n plus 1. N plus 1 is 10 plus 1 because you have to include 10, yeah? If if you put just n here, so it will be till 9 because 10 is not included here in Python. If you want to put the 10 included in here, then you have to put n plus 1. So this is how we created a range of x, then range of y. So this thing, this formula, we just put it in y, and then we just visualize this, and we saw how much is actually the probability of getting 5 hits, and how much is that probability. Now look at this probability. This is the probability, 25%. So the highest probability achieve this actually 24.6. It is like this. So this is how binomial distribution works in each of these or discrete um, uh, events. Now, this is how you have independent events, and then you're looking at these independent events um, with separate probability values. But if we have, for example, again, from SciPy uh, stats library, if we insert norm, which is normal distribution formula, there we don't have independent events, we have continuous events, but we have mean, which is very much important, and we have standard deviation. It's dispersion of data around the mean. So this is how you can understand that. Now let's generate data, for example. So it has generated a data, a line space. This is an NumPy function from -4 to 4. So -4 to 4 with the 100 points. Then norm. This is how you can call this function. Norm.pdf x is actually this line. Mean in a standard deviation. Mean is 0 in a standard deviation. So this is mean. This is 0 in a standard deviation. So if you plot it, so it will be having like this. This is how you will be having a distribution. But in order to understand proper understanding of these distribution, we will be playing something. Let's to the end. Do it to the end, because if you do it to the end, it will be easy to understand. Just let's start with rolling a die. You know what is die, yeah? It's type of سابق كان مسويني بس أنا شغال برنامج جيم اللي أدوية شوف بيقعد مش يعني يدوش يعني كل جيم لو دو صوتي دي كده التليفون هيفوت.
Yes.
So this is a probability distribution for a discrete. It's a very simple one. It's look at this. If you have a die and you're rolling a die, yeah. So each possible outcome in each scenario. Look at this. How many possible outcomes are there? 6, yeah. For each number, in order to get 1, in order to get 2, 3, 4, 5, 6, yeah, each side, in order to get each side. What is the probability? It is 1
1.
by, yeah,
1 by 6.
So now let's calculate the mean of this, yeah, expected value of a fair die. Fair die, what's fair die? What's an even die? Fair die, it means every time, without any bias, whenever you're rolling a die, so a number will be appearing. So there will be no specific side, for example, a weighted side. So no weighted side will be there. So all the sides will be even and equally, and that's called fair die. So if you just flip a die, roll a die, so what will happen? In first scenario, first one, you will be having on the first one, 1 by, how much is the probability? 1 by 6, yeah? The second round, we will be 2 by 2 multiplied by 1 by 6, yeah? Similar, so the whole this, if you just, uh, you know the addition in multiplication rule that we studied previously, yeah? Based on that, so the mean average of this distribution, this is called distribution, yeah? This is similar to a histogram. You know, this is 6 times, this is 6 number, this is 5, this is 4, this is 3, this is 2, this is 1. Yeah, so that's the average, the mean distribution of the mean of this probability distribution is 3.5. This is how you will be understanding the distribution. Now let's a bit uh, visualize it. Maybe you will understand it properly. That so if you visualize it, so this is the probability, and this is the first time, second time, third time, fourth time, sixth time. Yeah. So for each time, how much is the probability? Probability is 1 by 6. This much is actually the probability. So this is the probability for each time that you're rolling a die. Okay. Now tell me how much will be the probability of a die? How much will be the probability of a die if you're rolling it? The probability of a die equal to 2 or less than 2. How much will be the probability of it?
So it's 1 by 6, 1.
So how much will be this one?
Isn't it going to be 0.16, sir? Or are we going after the expected value of a fair die roll?
Anyone?
Maybe 1 plus 1 by 6.
Ashley?
It could be actually 1 upon 6 and 2 upon 6 plus, I mean.
Okay. No one is actually responding. Maybe either you are not paying attention
Sir.
or you are busy
Yeah,
or
I
you
did
don't
say
know the
something.
response. But it's
Hi,
very easy.
sir.
Look at this.
Yeah. Did you mean that it's going to be the expected value of 1 and 2? So it's,
If
yeah, it's
you are
going.
doing a roll, look at this. First time you die a roll, yeah? So 1.6. Second time 1.6. Third time 1. Now, what is the probability of dying a roll? Which should be less than and equal to 2. It's very simple. Less than and equal to 2. So first is 1.6 plus. Second is 1.6. Adding both of them, it will be 1.3. So these areas, if you're adding to that, that will be the probability of dying a roll whenever it's less than a specific. That's called even even die. Even die, a fair die. Fair die means that whenever you are dying a roll, so it will be equally landing one of sides. But there is also another thing which is called uneven die. Uneven die means, okay, one of sides are heavier. So one side is heavier. For example, side number 2, where the number is 2, is actually lighter in weight, maybe, or maybe on other sides you have equally put some weights, but on side number 2 you don't put any weights. so internal within this die. And whenever you're rolling, so 2 is not appearing all the time. Number 2 is not appearing all the time. And this is why this is called uneven die. So maybe in whenever you're rolling a die, in whatever dice that you're playing with, that's fair dice. So it means all the time whenever you're rolling, all sides are having the same weight. But if one side is not having the same weight with others, so that's called uneven die. And look at this, for example, first time we die and it become 1.6. Yeah. Second time when we die, number 2, which is the second phase that has to be a pair, it's not appearing. So that's 0. Number 3, look at this. In number 3, not 1.6, but 1.3. Why 1.3? Because the probability of number 3 is twice, because number 2 is not appearing. So 3 by 1.3, not 1.6. The remaining is the same. So the mean is a bit changed now. Previous mean was 3.5. This mean is actually 3.67. So the mean has been increased in uneven die. And actually, if you're just visualizing it, it's the similar like in histograms that you're having. Yeah. So previously worked with, or you just saw it. It's like that. Like this, for example. See here in this even die we have everything equally. Yeah. And here number 2 is not appearing. It is a biased rolling. So number 2 is not appearing. Number 3 is appearing twice instead of number 2. So this is 1, and this is how the probability changes. Now tell me, what is the probability of uneven die roll less than or equal to 2? What will be this probability according to this visual uneven die?
1 divided by 6.
It's 1 by 6.
Yeah, same answer, sir. It's going to be 1/6.
1 by 6, and another one is like
Okay, no one is
0
no
by
one is
6.
responding,
0 by 6.
and that would be again
1 by 6 plus 0 by 6.
Not 1.3 as it was previously, but that would be 1.6 because we don't have now number 2. So number 2 is not there. So it's 1.6 plus 0, which is there is no number 2, and that will be 1.6. This is how the differences between the probability of even and uneven die. So now let's understand it. This sampling and this rolling a bit differently. For example, let's do it in another way. If we have a die, let's visualize this in Python. If we have a die of, for example, this is die where it has 6 sides. In probability for each side, the probability is actually is equal to 1.6 by 6. Yeah. So if we just print die, if we just print it, what will be? So it will be probability for each side. Yeah. 1.6 is actually this one. This is the number, and this is the probability. This is called the probability for each side. Yeah. So you now understand how the probability works for this side. Now let's roll this die 10 times. Yeah. So if you roll the die 10 times, what will happen? rolls 10 will be actually make a sample of this die 10 times and replace. Replace is very important. We want to know either sample will be replaced or not replaced in each die, you know, in each roll. That's very important. That's very important, because if you make it false, then it will be it will be dependent even. If you make it replace it true, it will be independent even. So each time whenever you're rolling, so you're rolling again with all the numbers existing, so from 1 to 6. So it means you're not excluding anything. So evens are independent. So this is how you can roll a die with the 10 samples and see how rolls 10 look like. So first time when you rolled, number 4 appeared, yeah. Second time, number 5, number 6 appeared. So the same thing. So whenever you are dying 10 times, this, so this is 10 times that you have rolled a die, and different numbers appeared in these different times. Now let's see, for example, just in p dot mean of this die, yeah. So the average of this die is 3.5, and it should be 3.5. Why? This is how we calculated that it will be 3.5 all the time whenever you're rolling. That will be 3.5 all the time whenever you're rolling it. And let's visualize this, yeah. Just visualize rolls 10. Rolls 10, and we will be visualizing the number, and from the number we will leave the number column. We will be visualizing as a histogram, and within the histogram, the beans will be np dot line space of 1, 7, and 7. plt dot show. Why 7, 7? This is 6. We have to put it so this is whenever you're rolling a die 10 times. See? So in these numbers, we don't have number 1. See? Number 1 didn't appear, but other numbers appeared this much time. Number 5, for example, appeared several times. Number 2 appeared 2 times. Number 4 appeared 2 times. Yeah, 2 times. So this is how the probability of these different numbers, or their appearance and probability of different numbers in this histogram is there whenever you're rolling a die. So this is how theoretical whenever you're rolling a die, yeah. So this number is actually very close to the whenever you're rolling a die, yeah. Okay, now if you want to 100 times roll a die, so let's visualize it and see what will happen. Mm, Again, same thing. This is the visualization of 100 times if you're rolling a die. And what will be the mean of it? NP, mean of rolls 10. Number, yeah? And NP dot mean of rolls 100 number. So whenever you're rolling different numbers, so different means you will be receiving. And uh, uh, 3.43 and 3.5. So it's almost equal. So whenever you're increasing the number of samples, whenever you are rolling several numbers of that specific number, theoretically we have 3.5, yeah. Um, but this is the theoretical number. So whenever you are increasing the sample times and whenever you are rolling too much times a die, the mean of samples uh, becoming very close to the mean of population. So this is how whenever um, you're repeating a sample several times, so that mean will be much more closer to the mean of the theoretical mean, original mean of the population. So first, yesterday we learned that based on sample inferential statistics, you can, based on the statistics of samples, you can decide on the statistics of, on the parameters of population. So this is how you can derive several samples and then calculate the mean of all outcomes of that sample, and then understand how much will be the mean of population if you don't know the mean of population. For example, you want to conduct a survey for a population of, for example, 40 million people, but you have only a sample of 1,000. Yeah, you're doing that, but now it's coming that this 1,000, if the mean of this 1,000, however, this is not now we will be discussing later on what's statistically significant sampling. It is statistically significant or not, but that will be something else we will be discussing later on. But still, I'm just assuming that you will be understanding it theoretically. That whenever you're doing samples, one time sample, 1,000, then another time, another sample, you choose another 1,000, another sample, another time, another 1,000 people. So different times of sampling you did, and each time you're getting a result from it, then you're getting the average of that result, of all those results together. It gives you a parameter of a population. So you will be understanding how the population thinks, for example. Whenever you're increasing this sample and doing it several times, so this is how you will reach to the characteristic parameter of that population. This is how law of large numbers means. So it means that whenever you're conducting several times of experiment, several samples, several times you're doing sampling, the mean of all those distributions is actually very close, getting very close to the theoretical mean of the population. This is how you have to understand the probability distribution. This is called binomial distribution. So whatever we have learned right now, this was part of this binomial distribution that we just got it with a very simple this ones. So this is the type of binomial distribution that we learned it there, and I just explained it in a very detailed one, that how binomial distribution means. It means discrete distribution, which probability of k-successes in independent trials with probability of p. So this is how we just die-a-roll, and then we visualize the probability of having those rows. So this is this much time we get in this 100 times we die-a-roll. So in 100 times, look at this. So we got 6 only around 15, 16, 17 times. We got 6 in 100. We got 1, for example, 25 times. So this is how it works. Here, for example, we die 10 rolls, yeah? 10 times we die, we roll a die. Here, we just got 5 several times. We got 5 3 times. And we didn't get any one. So there was, we were more lucky here than here. So, but still, this is why the mean is decreased here. See, this was 3.5 and this was 3.43. So we were not much more luckier in this rolling die. So this is how you have to understand the binomial distribution, and whenever it comes to the discrete distribution, the discrete distribution. Discrete distribution is actually the functionality to binomial distribution. So let's discuss something else. That's continuous distribution. So what's continuous distribution? Just assume this one. So you're waiting for a bus, yeah? From 1 p.m., 1:12, 1:24, 1:36, 1:48, and 2 p.m. So these are times, wait times, yeah, minutes for a bus, yeah. So waiting times. So this is called continuous uniform distribution, yeah. So you're waiting for a bus. Like this, wait time of minutes, yeah. So this will be 12 minutes here, yeah. So 1 p.m., 1:12, another bus will be. So if you're standing from wait time, so 12 minutes, for 12 minutes, this is wait time will be, and that would be 12 minutes each minute, and that's a continuous minutes, yeah. So if 12 is the total number of outcomes, so waiting 1 minute is actually 1 by 12, yeah? So probability will be 1 by 12. You got what I'm saying or not? I have to explain it again. So you have 12 minutes. This is 12 minutes. Each minute you're waiting, yeah? So probability of waiting for each minute is 1 by 12. That's 1 by 12. But what is the good thing about it? And what is the difference between the other ones? That you're continuously waiting, yeah? So each minute you're waiting. So it's continuously you're waiting till 12 minutes in order to get to the bus. Now look at something else, for example. What will be the probability of wait time between 4 minutes and 7 minutes? How much will be the probability of time between 4 minutes and 7 minutes? Look at this now, how it's going to be calculated. It's a bit different from discrete calculation. Here, area is very much important. You have probability of area 4. This is area 4. 4 is included, and 7 is also included. So you have 4, 5, 6, and 7. So what will be the probability of waiting times between and equal to 4 and 7? So this area actually. This is how you will be calculating the probability of area between 4 and 7, yeah? And how you will do that? So this is now calculation of area time, because you're continuously waiting, and your events are dependent, not independent. It doesn't mean that 1 minute you're 1 minute is independent than another minute. No, all minutes are dependent to each other. Now look at this. 7 minus 4 is 3, and probability, which is a continuous probability, it is 1.12 for all these minutes. So 3 by 1 by 12. Look at this now. You will get it proper understanding. Three by multiplied by 1 by 12. So this, if you multiply by this, you need the area of this square, yeah? So you have to multiply this by this. And this is how the probability of waiting time between and equal to minutes of 4 to 7. And this probability is actually, this is a continuous probability wait time. So now tell me, what will be the wait time less than 7 minutes, less than and equal to 7 minutes?
Ah, 7/12, sir.
Okay, it's okay. If no one is responding, I will be coming to that. For example, that how will be the probability of time for this one, for example. So less than 7. So how will be the probability? In Python, you can very simply calculate it, and that's called a function. It's called uniform.cdf. You have to first insert from scipy.stats import uniform. So I have to insert code here, not text. And then after that, you can just simply uniform.pdf and put everything there. So we need 7 included, less than equal to 7. Yeah, so this is just from 7. This is the total is 12, and 0.8, 0.6 is actually 60% is the probability of time that you have to wait. This is one of the things. Another thing is actually probability of time. If you want to know it, for example, not less than, but larger than 7. So if larger than 7, you can just 1 minus this one, so the remaining area you will be getting the remaining area. This is how the Python can calculate to you the probability of different areas. This is the library that you can use. So you have 12 minutes, and for each minute there's a probability of 1 by 12, and this is how you're getting the understanding of how to continuous probabilities work. We have different types of continuous distributions. We have, for example, continuous variables, continuous type of distributions. And for all these continuous distributions, the area is very much important and playing a key role. And here in our lecture, this was the continuous distribution that we studied. This is called normal distribution. This is type of continuous distribution. It's called normal distribution. So this is how we will be focusing, and I hope you got understanding of what is the continuous distribution and what is the discrete distribution, binomial distribution, and normal distribution. Now we will be looking to another chapter, which is one of the important chapters here, and in normal distribution, and that's very important, because in normal distribution, all the time we are talking about the mean. Mean is very much important here, and standard deviation is very much playing a key role. And area under the standard deviation, so it's also playing a key role. In what's standard deviation? Actually, standard deviation is the area which is around the mean. This is how we can get it. Sometimes we have discrete distributions, and discrete distributions can also be acting like a normal distribution if it fits under these curves. If it fits, then it's type of normal distribution. Now coming to the one of the main and important topics in the probability, that's called central limit theorem. And what's the central limit theorem? The definition is the central limit theorem states that the sampling distribution of the sample mean approaches a normal distribution as the sample size increases, regardless of the original distribution of the population. This is the thing that we have already studied. Yeah, if you're rolling a die 100 times, so the mean of that sample is getting closer to the mean of the population. Whenever you are repeating the sample several times, so it means applies to large sample sizes and works even if the population is not normally distributed, and important for inferential statistics. It's why important. Central limit theorem is why important, because whenever you are having several samples, those samples can be if you're increasing the number of samples and then you're calculating something statistically for that sample, then it automatically applies in getting very closer to that specific characteristic and parameter of the population. This is why sampling is very much playing a key role. How to get a sample from a population and how the sample should be. For example, there. Look at this. We have a population, exponential population. So this is how we size of 10,000 we generated a non-normal population. Then sampling size. We don't know the sample mean yet. Sample size is 30 and number of samples is actually 1,000. Now look at this. This is how we just got the visualization of population distribution. So this is the population distribution. This is the population distribution visualization, and this is the sampling distribution of the mean understanding of that. So these distributions are maybe not the same somehow because this population is actually skewed to the right very much, but still, if you're looking at the mean of these two ones, means are getting closer and closer. If you're look at the sampling is already also toward this, yeah, but this is only for 1,000, and this is for 10,000. So if here you are increasing the numbers, this is also will be skewed to the right and will be shifted to the left, slowly, and will become like this. So you see, this is how it calls central limit theorem, that sampling characteristics, statistics of sampling is actually giving you the understanding of a population, for example. This is how you get it. So as we roll a die several times previously, you saw that. So if you just 10,000 times you're rolling a die, it gets much more closer to the theoretical mean. It will be closer to the theoretical one, which is 3.5. This is how you have to understand the central limit theorem, and this is a very simple thing. There is no need to just be very much complex about it. But however, everyone just whenever you're looking at it's type of law of large numbers. That's it. So we will be having different types of distributions. We will be not going to that, but we will be just going to the other topic of within this probability. That's also one of the important topics within the probability. That's called z-score and standard normal distribution. So we got what is normal distribution, yeah. So we now understand that type of continuous distribution. But what is the z-score for that? Z-score is a type of number of standard deviations, a data point is from the mean. So it means if you have a data point z, z is larger than 0, then data point is above the mean. So if means this was a normal distribution, this was a normal distribution, and this was the mean of it, yeah. So this 0 equals 0 is the mean of it. So if z-score, if you're calculating a z-score and for a specific data point, and z is larger than 0, it means data point is above the mean. If 0 is if z is less than 0, then data point is below the mean. And what does it mean? It's number of standard deviations a data point is from the mean. So data point, and then if it gets how much it's far from the mean. Why it's important? Because we're comparing data points from different distributions. If you want to, if you have different distributions and you want to compare these data points together, then one of the good measures in order to compare these data points from different distributions, it is the z-score. You have to find z-score in all these distributions and then compare those data points and see how z-score affects. So it's below mean, it's above the mean. So how is that? It's closer to the mean. Closer to the mean is good. Below to the mean is it depends on how you will be assessing that. So this is your understanding. Also, z-score is affecting the outliers as well. For example, sometimes instead of IQR, you can use z-score for detection of outliers. For example, you say if a point is 3 times far away from mean of that distribution, so I want to consider it as an outlier. And why this absolute value? Absolute value is playing a key role here because it means that either to the right of the mean or to the left of the mean. So either to this side or to this side. So not important. Both sides, if z score is, for example, is larger than 3, it means it's 3 times far away from the mean, then I want to consider it as an outlier. So this is how z-score is also playing a key role for detection of outliers. As I mentioned yesterday, detection of outliers are playing a key role whenever you're assessing and analyzing the data sets. And why it's important? Because you will be deciding either you have to eliminate a number of data observations or data points or not. So because if you're just eliminating that, so it will be affecting seriously the mean, the median, the mood, and the whole summary statistics of that specific data set. And also, z-score is important for calculating the probabilities using the standard normal distribution. So if we have standard normal distribution, so z-score is also playing a key role to just calculate. For example, we have a data set of 60, 70, 80, 90, 100. The mean of this data set is, and also the standard deviation of this data set. You have to find both of them and how to then calculate the z-score. Z-score is actually each data set, each data point minus mean of the whole data set divided by standard deviation of that data set, standard deviation of that data for x and data. For x and data, so each this one. So it will be calculating the mean, the z-score for each of these data sets. Now look at this. We have 1, 2, 3, 4, 5. Yeah, 1, 2, 3, 4, 5. So 5 z-scores here for each these of elements. Look at this. Number data point x1. This is x1. x1 is minus 1.4. This is the z-score for it. x2 is, which is 70. It is minus 0.7. ET is actually 0. It means this ET is actually the mean. It means it is mean. It is closer to the mean, or actually it is the mean. And 90 is 0.7 and 100 is 1.4. So it is type of an equal normal distribution like this. See, there is the mean, and these data sets are like this. This is how you will find. This is the formula of z-score in Python. This formula. So each data point minus mean of that data point divided by standard deviation. And that's the standard deviation. So you have to find these ones. So also from SciPy statistics, if we have a z-score for a data point, for example, for a data point, we have z-score of 1.96. Now, probability of being less than z, for example, yeah? Now, probability of that, we have to use the normal distribution here, norm.cdf of that z-score. So let's probability of being less than z is 1.96. It's almost 0.97. And probability of being greater than z, 1.96, is 0.025. So this is how it says the distribution z-score for a data point. You have a z-score of data point 1.96. Yeah. So this is 1.4 is for 100. Yeah. So you have a probability. You have a z-score of 1.96 in a data set. And you want to know how much data is greater this data point, and how much data is less than this data point, the probability of how much data. So this is how you can calculate the probability of being less than z. It means that almost 97% of the data points is less than z, less than 1.96, and only around 3%, 2.5%, is larger than 1.96 of this z-score. So this is how you have to understand the z-score. Now let's come into the hypothesis testing in understanding what's actually the hypothesis testing here. Hypothesis testing is often uses the standard normal distribution to calculate p-values. And example is actually testing if the average height of a group matches the national average. Yeah. So this is how, for example, hypothesis. This is called hypothesis testing. This is how step and error. So this is hypothesis testing. This is null hypothesis. So, and this is alternative hypothesis. This is how testing is. So this is, look at this. This is normal distribution. Yeah. And this is the area where H0 is accepted. So this null hypothesis is accepted. This is the area which H0 is rejected. So rejection region is that alternative hypothesis is actually accepted. And z-score is playing a key role into that. If you have a number of, for example, sample heights, these are the heights of people in fruits, yeah? Then sample of these heights is these ones. Then population mean is actually 5.5. So population mean average height is 5.5 all over, yeah, a population. This is hypothesis. Hypothesis says that, okay, average height is 5.5. It means if we have a population that we cannot go and check the height of each person there, yeah, but we are assuming that it is just 5.5 on average. Then we have a population set of sample sizes. This is our sample sizes, and this is sample sizes. Now, for the sample size, we have to find standard deviation. So this is how we calculate the standard deviation. Then for the sample size, for example, this is the size of our sample, length of sample heights. So 1, 2, 3, 4, 5. So this is 5. 5 is the length of this list. Now calculate the z-score. How to calculate the z-score? Sample mean, which is the mean of the sample of these people, minus the population mean. So we have to minus the population mean divided by sample standard deviation by square root of sample size. And then we have to print the z-score. And this is the z-score. Z-score is actually 0. And what does it mean? It means 0. It means that the population height average and the sample height average is actually equal to each other. And what's p-value? P-value is actually it's calculate the p-value. It's 1 minus normal distribution of absolute value of z-score by 2. So this is how you have to understand. Sometimes you don't get it, the z-score. Z-scores may be sometimes minus. P-value is actually the absolute value of that specific z-score. P-value in z-scores are equal like variance and standard deviation. Actually, variance is the distance between points and between the mean. But sometimes variances gets negative values as well. This is why you have to introduce the standard deviation, which is the square root of that minus value, negative value, in order to make it positive. Here, the z-score in p-value is also the same thing. This is how you can get and understand how to calculate the z-score even for the hypothesis testing. Now we are entering to the inferential statistics and its application. So these are all things that we have studied till now. This is part of summary statistics and descriptive statistics. These are all calculations that we have made. But now, right now, we are going towards some, and we understand also the probability of different events. After this, we will be entering toward the prediction of something. So now you have a proper understanding of how statistics works, how probability works, how chances are there. So whatever previously you were saying chances, now you understand that those chances are called probabilities. And after this, we will be entering to the inferential statistics and its application, and we will be studying the we will be entering toward the predictions. So, and then after this, inferential statistics, it will be the basics for the regression. Regression is the basics for the forecasting, and then we will be going toward the model development, machine learning. And what's actually machine learning does, it is actually predicting the outcomes and the future values for something, for any event, or if it's time series, or any model, different types of models, or anything. So this is how we will be going from the current statistic, from the current state of data toward the future state of data. We have a data set. Now we understand properly how the data sets works, all the statistics aspects of that data set we have, and we understand it properly. Now we have to understand, okay, now we have this data set, how, based on this data set, we should predict something that it will happen in the future, based on the current data that we are having. So let's have a break of maybe 5 minutes if during this break you have any questions, because I understand that these are some complex theoretical things and technical things. Sometimes it gets frustrated for the students and as well to understand it properly. So I'm just saying that please don't worry whenever you're working during the modeling, during the machine learning model in prediction models, you will be experiencing all these ones, but still you have to have understanding of these theoretical terms as well. Any questions, please? Is there anyone? No one is responding to my questions, actually.
Yeah, we are here. I think everyone understood, so maybe there is no question.
I don't hear any of you. Yeah, so no, my microphone is working very well. What is the problem? The point is that I cannot hear you. That's the problem.
Can you hear us now?
No, I cannot hear you guys. Let me. I will just stop this call and will join again, because
Can you
if I
hear
don't
now?
hear you, then it means.
Hello, sir. Can you hear me?
There's a problem on my side. I don't know. Everything is on my side. It's the same as it was
No, sir.
yesterday.
No, sir. No, sir. Everything is fine from your side. Maybe you hear my voice also.
بله استاد صدای شما شنیده میشه.
No, the problem is that I cannot only hear you. That's the problem. I can hear the notification sound of if someone is entering, going out, asking something. So those notifications I can hear properly. Just leave the call coming. Please talk, someone.
بله استاد صدای ما رو داریم؟
Now, yeah, I can hear all of you.
Okay, great.
That's very bad. I didn't hear any of you. I was thinking that no one is actually participating in the lesson.
We have been participating, sir. Every time you were asking questions, a lot of people were talking as well.
But you didn't. You didn't just saw that there is no. There's nothing from my side. Maybe I don't hear any of you. That would be the problem.
Yeah, we did notice, sir. Don't worry. We were just chatting about it on the chat box earlier.
Good. Any questions? Because I just say that we will be waiting for. Oh, the chat is already clear, but still, if you have any questions just within this break, we can.
Yeah. Danish, sir, said that if you could possibly recommend some Persian resources regarding probability as a topic. So that was the question before you left the call.
One of the problems with the Persian resources is that it should be find the resources which are very much relevant to the data analytics side, because I really don't want you to go deep into the probability from the mathematical statistical point of view, because it has a huge area of application. If you go deep into that, I think you will not be studying anymore these things, because it's a very difficult topic. We learned probability long time ago when we were studying in engineering. So probabilities is a wide subject which almost all technical faculties, they are studying that. Engineering, for example, also, so they have other types of its application, very complicated type of its application. But we have to find something which is very much relevant to the data analytics, and still it should be simpler. We will try our best. We will see if something is there. But still, I hope that the current lectures that we are having, it helps students, and then it helps you as well. But I will try to find something for you. No worries. I think from engineering faculty, I can find something from you. Maybe I will contact some of my previous colleagues. Emal Amiri, you have a question, please?
Yes, sir. I just wanted to ask, like, these are like the probabilities, like looks like the random numbers, or like picking something randomly. So I mean, like when the computers are like taking random numbers, they're just producing it. Okay, so additionally you said like this is something that machine learning is using. I mean, the probability is something that machine learning is using it. That's like uh, using it for like predicting things. So I'm confused, like how these random kind of things can be like predictable.
No, look, you cannot generate probabilities randomly. You're generating data sets randomly. And there is a difference. We are not generating probabilities randomly. You cannot generate probabilities randomly. Whatever random we have generated till now, it was type of data that we have just developed some data, some theoretical data we developed
Sorry,
in
but
order.
like when we are like using the dice example in there, like from 1 to 6, like
Yeah.
each time when you run that
I don't hear you, Imam John. I think your voice has been disconnected. Uh-huh. Your voice has been disconnected. I don't know. It's again with me.
No, your voice is here. We can hear your
Good.
voice.
Uh-huh.
Maybe he has internet issue.
Yeah, maybe that's it. Yeah, I can the point is actually, so no, rolling a die, it's randomly. But random thing is something else, probability is something else, and prediction is totally something else. If you're rolling a die, so you don't know it will be 1, it will be 2, it will be 3, it will be 5, it will be 6. How much it will be? You don't know it, yeah? But for each of those values, you have understand a probability. There is a chance. How much chance that you will get 6 if you're rolling a die? This is called probability. Probability of a random rolling die. Yeah. So this is how. But it doesn't mean in that probability is always there. But you're just not considering that. So that's type of if you're just giving me an example of randomness, because you don't know exactly the outcome of that, but you understand the probability of it. You don't know if you're rolling a die, which number it will be, number 5 or 6. You don't know it, but you know at least the probability of it. That each times, if you're rolling a die, the probability is around 1.6, 16, 17%. That it will be 1, or it will be 2, or it will be 3, or it will be 4, 5, 6. This is how probability works. And this is how random things work. And we generated some random data. So those random data are just for simulation sometimes that you have to understand it. For example, we are saying central limit theorem. For central limit theorem, we are saying that we have to roll a die 1,000 times. So you have to do it with the computer, yes, 1,000 times. You cannot just do it yourself. You can do it yourself, but you have to just waste a whole day sitting there and 1,000 times roll a die, yeah, and record everything. So that's type of random actions that random observations that we can generate. Model development and prediction is totally different thing. Actually, they're using those probabilities. They don't have anything. They don't have anything with the randomness. They're working with the probabilities, and probability is there actually. Even if you have a random rolling die, which you don't know the result, but you understand its probability. Yeah? You understand the probability is 0.1617. or around 17%. So that's known. That's for all those 6 observations. It's applicable. This is how it will get toward the forecasting, toward the regression modeling, and toward the model development. So this is how it is there. And please don't be confused whenever you are going to the model development in machine learning, then you will understand. One more thing which machine learning is actually doing, it's not actually using absolute probability to predict something. Machine learning is actually is not about predicting something based on probability. Machine learning is predicting something based on the existing data that we have. So it analyzes the current data that we have. It analyzes the current relationships between those data that we have. It analyzes the links between those features. It gets all those things, and then it analyzes the impacts and effects of exactly when it says and finds the patterns. Then it finds the patterns between those features and sees, okay, if this feature 1 is increasing by 2, feature 3 is decreased by 1. Feature 3 is increased by 1, feature 5 is increased by 6. This is how it finds the patterns and memorizes all those patterns and put it in a model type. We are saying that we have developed a model, and that's the model. Model learns it, and whenever you are giving a new data to the model based on those patterns, giving you a new prediction for that. So it's actually not that much probability, actually. It is type of understanding the patterns as well. But the probability is the basics of all those understandings in learnings. I hope your question is now somehow
Yeah, it makes sense.
answered. Yeah.
Thank you.
The words with higher probability are preferred than others. So ChatGPT uses probability to generate words. Actually, not probability. It's somehow it's something else. Oh, we will not be going toward the LLMs, large language models, but it's not type of probability. It's type of similarity. It's searching similarities. You understand that the computer doesn't understand the words, yeah, and computer doesn't understand the alphabets. So everyone understands that. So what's happening with the large language models? Whatever data you are having they are putting it in a vector database. Vector database is actually type of arrays, numbers. They don't know about the word. They don't know about the alphabets. There is nothing about the alphabet, about the word, about that. They don't understand the context. So they don't know what does it mean, for example, a word. That's not their problem. They don't understand the machines. They don't understand that one. They're putting those data into a vector database. Vector database is assigning actually numbers to all those. So there are large softwares and ways of doing that. So whenever you're asking something from an LLM, that LLM is actually again getting your text, putting it in its own type of vector database. It means that LLM is actually changing your text into numbers again, and then finding similar, closer. It's called lots of these LLMs. They're using cosine similarity. Cosine similarity is one of the things that we will be not discussing in this course. But if someone interests to continue their education toward the data science, then that will be part of data science. Then, based on that cosine similarity, they find the specific words in context, specific numbers there, and then put that number again toward you, and that number is just again converted to alphabet to you. This is how computer works. So it's not type of probability, actually, it's type of cosine similarity. Not only cosine similarity, but type of similarity. In vector databases how it works. They are calling this transforming text to numbers and numbers to text. It's called embedding. Okay, we will be now coming to the inferential statistics. Inferential statistics actually getting a sample from a large population, then analyzing the sample, then based on sample, make some predictions for the whole population. This is a very simple way of defining the inferential statistics. We have different types of samples. How to choose the sample? It's very important that you have to choose proper sample. If you don't have, if you have a biased sampling system, if you're selecting a sample, then you're predicting something for the whole population that would be very. For example, I give you this example at the very beginning of this lecture when we were discussing the biases. What is bias actually? For example, you're predicting something. You want to predict. You want to develop something for farmers, yeah. Which is, for example, more than 10,000 farmers in a specific province, yeah. But you're doing a survey in an urban area with people who are just, they don't have any understanding of farming in agriculture. So, you know, that's a biased decision in that sampling that you got that sample. It is actually very irrelevant. And based on those samples, if you're predicting something and then applying that to the whole population, which is the whole farmers, and then you're saying, oh, this is good for the farmers, then that would be a very bad decision, the policy decision making. This is how it works in all over aspects of our life, starting from our personal life to the social life, the economic life, even political life, whatever decision at the country level, at the world level, so global level, whatever is there. So this type of sampling is very much important because you have to understand how you will choose the sample in order to derive something from that sample and then apply that to the whole population. This is how the whole thing of inferential statistics is based on that, and it's relying on that. Now, we have sampling techniques and we have sample size distribution. So what is sampling techniques? We have random sampling. Each element has an equal chance of being selected. So this is a simple random sample. Look, we have these people, and then he says, okay, randomly we are selecting some people, yeah? Just randomly. Okay, we just selected some random people. One, then this guy, and this guy, then this guy, then so these are a random selection of people. So everyone has an equal chance of being selected. So the probability in this case is equal with each person. It is type of rolling a die, yeah. Rolling a die, probability for each number appearing is equal, yeah. It's 1.6, 1 by 6. So this is how random sampling is actually working. This is called random sampling. Now, coming to the stratified sampling, what's systematic stratified sampling? Stratified sampling is actually population is divided into strata, and samples are taken from each one. So this is strata. Look at this, and then samples are taken from each. So this is how stratified. So look at these were the numbers, yeah. Now what they have done, they have divided these ones, these groups, then these 1, 2, 3, 4, 5. These are 5 theirs, 3 there. Then 3, 4 blues are here, 3 greens are here. So from this set of strata, they selected this one. In the second, and another in blue one, they selected second. Here the second. Here they selected two more ones from the blue ones. So 3 from blue and 2 from green. So this is how they got some samples are taken from each other. So this is how stratified sampling works. How is systematic sampling? Select every cat element. So for example, systematic sampling. So I want to select this number. I don't want to select the second number. I want to select the second number, not the first number, the second number. Then don't want to select 2 numbers. I will just remain these two numbers, select the third one. Again, two numbers, then third number, third one. I will just remain two numbers, select the third one. Two numbers, select. So this is type of systematic sampling. You're putting a pattern for yourself and you're saying, okay, not the first guy, I will select the first guy, then not, I will not select the second and third guy. I will select the fourth guy, and not the fifth and sixth guy, so seventh guy. So this is how I will be selecting the samples from the population. That's called systematic sampling, that you're preparing a sample. And what's cluster? Population is divided into clusters, and clusters are randomly selected. Now, cluster sampling is actually you're clustering the population based on something, and then what is the difference between a stratified sampling and between cluster sampling? In a stratified sampling, in each cluster that you have put here, you have to get one sample from that cluster. In cluster sampling, actually, you divide population based on clusters, and then you're selecting each cluster, for example, the whole cluster. You have to select the whole cluster. Now, how to do those clustering? That's totally different things. That how to do that clustering. Sometimes you have to do it, but sometimes if you don't know how to do it, then computer can do that for you. For example, maybe you heard about KNN clustering in computer modeling. Then we will be coming to that in how that modeling works actually. This is how clustering, for example. This is different types of sampling, and you have to understand whenever you're doing something, you have to understand how to do it and how to understand the sampling. Now let's see, for example, I have a population, and range of population is from 1 to 101. It means my numbers within this population is 1 to 100. Yeah, so I put 101 because 100 should be included in there. Random sample size of 10 people. So this is random choice. NP, random choice. Population size 10, replace false. Look at this. This is just sample. Randomly you selected 10 sizes from this population. This is the random selection of population. So this is computer also doing for use this random selection of population of sample from the population. This is how Python is good, and Python helps you whenever you're having problems. See how it will work. You got how to choose the samples?
Yeah.
Very good.
Yes, sir.
Very good. Now coming to the confidence intervals and concepts and calculations of what is actually confidence intervals. Just wanted to share my whole screen, but I really don't know how to share it. Okay, I will not waste the time because we have less time. We will be proceeding with the confidence intervals. And discussing what is the confidence intervals of that, and what's the concept and calculations of it. Confidence interval, or CI, provides a range of values likely to contain the population parameter. You know what is the population parameter? It means you have a sample, and then calculated the statistics for that sample. And that sample statistics is actually acting as a population parameter. Okay, so that's type of population parameter. Then you have to understand, for example, how this population parameters is working. This is how you have to understand the confidence interval, and based on that, define something. Derive any decisions for a population based on that confidence interval, based on that sample. This is a simple formula for it. It means X is actually the sample mean. So you have a sample mean, you have a sample from that population, that's the mean of that, plus minus of that z-score for desired confidence level. You may hear, yeah, so that what's z-score, yeah? We just learn it properly. Then after that, we have to multiply that by population standard deviations, not the sample standard deviation, but population standard deviation, or sample standard deviation. If it's not unknown, then you can use also the sample standard deviation, and then the sample size. So that would be the sample size. So for example, we have a sample data. This is our sample data. The sample mean for this data, then sample standard deviation. You have to calculate the sample standard deviation for this data. Then the sample size. This is 1, 2, 3, 4, 5. 5 is the size of this sample data. Now look at confidence level 95%. What does it mean? Z-score is actually norm.ppf 0.975, two-tailed for 95%. Calculate margin of error. Margin of error is z-score sample standard deviation by square root of sample size. That will be margin of error. Now look at the confidence level. Lower bound of confidence level, it will be sample mean minus margin of error. Upper level will be sample mean plus margin of error. Now look at this. 95% confidence interval is what? Lower level is 48.6. Upper level is 51. What does it mean? 95%, we are 95% confident, yeah, that, for example, the mean for this population is between 48 and 51. The data, for example, for this population, or the size of this data, yeah, look, this is the size of this sample data, is between 48 to 51. And it's actually like that, yeah. So we have 51, and this is 52 is the highest, and 48 is the lowest. So this is the upper bound, and this is the lower bound. So how to show it? I think I have to show it in this. There was a picture. I'm just searching for it because there you could understand it very much properly. The confidence level. I'm just trying to search that picture for you because it shows you. That how the 95% confidence means. What does it mean, and what the 97% confidence means? So different types of.
Sorry for interrupting. So here is two-tailed for 95%. If it's, for example, it's one-tailed for 95%, is it like one of the 48 or 51?
Yeah, it's because because we are looking at you're looking at two sides of it, yeah. So
Yes.
that's the thing, that you're looking at two sides of this normal distribution. This is why you have to calculate two of them. You have to add two of them, yeah, together. This is the thing, because it's toward the both sides of the normal distribution. I found it. This is now, see, this is the 95% confidence level. So this is if you have a normal distribution, this area is actually, yeah. So this is the area. is that you're not confident, and this is another area that you're not confident, but 95% you're confident. And this is why it's called two sides, yeah? So two tails, this one tail and another tail. So 95% of you're confident that the data is actually within this distribution. This is how the confidence level means whenever you're calculating the confidence level and understanding the confidence levels. So I hope now you have understanding of what is actually the confidence level is there and why it's playing a key role. Because you have to find the upper bound for the confidence level and have to have understanding the lower bound. And this is the formula that you have to all the time understand. In order to define the lower bound and the upper bound, you have to have understanding the z-score, and you have to have the margin of error. So this is the margin of error that you have to understand. And then based on these ones, you can calculate simply the lower bound and the upper bound. So for that normal distribution that I just showed you that picture, 95%, it means this lower bound is 48.6 and upper bound is 51 from this data that we are having. So 95% of the data is actually between 48.6 and 51.4. This is how it works. Now coming to the hypothesis testing. And what is hypothesis testing? We have a null hypothesis. We want to test it. We say, okay, we have an assumption, and we want to see either we should change this assumption based on some statistical inferential statistics and select our alternative hypothesis, or not. We should continue the same way that we are having it right now. So hypothesis testing is a method to test an assumption, hypothesis, about a population parameter. For example, we have this is null hypothesis that we are having null hypothesis in alternative, which is HA or H1, H alpha hypothesis. We have to have a significance level. So typically 0.05. So on both sides, yeah, if we have that significance level, we have to calculate the test statistics, for example, z-score and t-score. And then we have to find the p-value and compare with alpha or 1, which in this case H1, and then accept or reject the null hypothesis. So then we should say, okay, you want to reject this, our null hypothesis or our initial assumption or not. There are two types of errors whenever you're doing it. Type 1 error is actually rejecting each one when it's true, yeah? And type 2 is actually failing to reject the null hypothesis when it's not true. It's actually while the alternative was true, actually. So this is how the hypothesis testing working. And the null hypothesis and also the alternative hypothesis testing. So testing works. For example, we have an assumption, we have a claim about a population, yeah, and we want to decide that claim or assumption is true for that population or not. For example, we have an assumption that okay, mainly, for example, women are living longer than men. So this is an assumption. This is a null hypothesis, actually, yeah. So men and women, it's very difficult for you now to just calculate the whole population of men and women, yeah, for a specific maybe country or a county, even for a village, even for a small neighborhood. It's very difficult. Now you have to get some sample data, analyze the sample data based on sample data and hypothesis testing. Then you have to decide either you're accepting this assumption or you're rejecting this assumption. What does it mean? If, for example, women are living longer than men, yeah? So this is null hypothesis. And now, based on this, you want to just change, analyze the data, and want to understand either you want to accept this null hypothesis or reject it. But there are two types of errors. One type of error is actually you're rejecting it. You're saying no, women are not living more than men. So this is, you just rejected the null hypothesis, while actually it was true. This is called type 1 error. What is type 2 error? Type 2 error is actually you're saying that, yeah, women are actually living longer than men. So you're accepting the null hypothesis, while alternative was true, which is men are living longer than men than women. You got the point?
Yeah,
So
you
this is the
reject.
difference. Huh?
Second type, you reject the null hypothesis.
Yeah, second time, no. The thing is, in the second time, in type 2 error, you're rejecting the H,
The null
failing to reject.
hypothesis.
No, you're accepting the null hypothesis. You're saying that women are living longer than men, while it's vice versa, which is the alternative one. That's true. It means no, men are living longer than women. This is called type 2 error. So this is how it means type 1 error in type 2 error. One of the critical things about type 1 and type 2 errors, or whenever you are dealing with the hypothesis testing, that's because type 2 error is much more dangerous than type 1 error. Because in type 2 error, if you're doing it, it means you're accepting something which is not realistic, which is fake. In type 1 error, if you're not accepting an alternative hypothesis, that's okay, not a problem. Yeah, okay, you're not accepting it. That's it. But in type 2, you're accepting a fake thing, which is not true. So that's more dangerous than that one. This is how different types of hypothesis testing works, for example. I can give you more examples of hypothesis testing, for example, in a very different way. And for example, and different things and on different ones. For example, I had a very simple example of hypothesis testing. I just give it to you in regard to the something. But let's assume something else. For example, if a shopkeeper, for example, just have a shop, maybe a bakery, for example. Just assume that there is a bakery, and that bakery is actually says that it claims that, okay, all the cookies or for example the breads that they are preparing, the weight is actually exactly 50 grams each one. And you want to test something, yeah? You want to conclude a hypothesis testing. Now, how to do that, yeah? Okay, what is H0 here? H0, which is the null hypothesis. Null hypothesis says that all the breads that this bakery is cooking is actually weigh 50 grams on average. Okay, but what is the alternative hypothesis? This alternative hypothesis, that's, it says that all the breads, the breads on average, which this bakery is cooking, is not 50 grams weighing. So this is the alternative one. You see, this is how you can put the hypothesis testing in. Then, first of all, before concluding this testing, you have to collect some data. Okay, let's take a sample of some data. Let's collect, for example, 30 breads. Buy some 30 breads from this bakery. Okay, and calculate their average weight. For example, we calculated average weight for that, and then we use a formula, for example, t-test, to compare the sample mean to 50 grams, for example, or maybe we can find a p-value for that. Suppose we find the p-value as well. Then our decision is, for example, that how, based on this decision, we should choose this. If if we got this one, and then alpha, for example, is equal to 0.05, then we say, okay, and we suppose our p-value is 0.03. It means our alpha is now larger than p-value. We say, okay, H0 is rejected. What does it mean H0 is rejected? It means that the bricks are not weighing 50 grams each one. But if p-value is less than 0. The alpha is less than 0.3, which is the p-value, then we say, yeah, on average, all the bricks are weighing 50 grams. This is how you can decide hypothesis testing and alternative testing based on the evidences that you're collecting and based on the calculation of the different types of values, for example, the z-score and the p-value. These are the steps that you have to take whenever you're doing a hypothesis testing. This is very important. You can apply it to the real life problems as well. This is why it's very important. Now let's talk about one sample and two sample tests. For example, t-test and z-tests. For example, one sample t-test, it means compare sample mean with population mean, used when population standard deviation is unknown. If we don't know the standard deviation of the population, we are just comparing the sample mean. We are comparing the mean of this sample with the population mean. That's called one sample t-test because we don't know the standard deviation of the population. And two sample t-test, this means compare means of two independent samples. We are getting two independent samples from that population, and then we are comparing two means. We have a sample data, for example, this is sample data of heights of different people. And we are saying, okay, this population within this village is actually the average of height of population within this village is 5.2 feet, for example. Now let's one sample t-test, conduct one sample t-test. Okay, t-test and p-value. This is the formula for that t-test. Okay, we have sample data. This is our sample data. We have population mean. This is our population mean. Okay, and just this formula will bring you the t statistics. So this is 0, p-value is 1. Conclusion: if p-value is less than 0.05, then reject the null hypothesis. Else, fail to reject the null hypothesis. Fail to reject the null hypothesis. It means fail to reject the null hypothesis. So it means here our p-value is actually equal to 1, and the sample mean here is equal to the population mean. So from this, sample mean is equal to this. So it means actually t statistics is 0 and p-value is 1, and then actually we are failed to reject the null hypothesis. And this is how it works if you are conducting only one sample test. And what is two sample test? We have that population of that specific village, and we got two samples. We got group 1 sample and we got group 2 sample. And then we are putting with this formula, t-test end. So this is the t-test 1 sample formula, and this is the t. So these are all formulas in the SciPy stats. If you put that and then put group 1 and then put group 2, now print the t statistics, t stat and p value. T statistics for this test is minus 3.4, and p value is actually 0.003. So this is how p value is actually less than 0.05. Then we can reject the null hypothesis. This is how from two samples we get to reject the null hypothesis, and this is how you can calculate the hypothesis testing based on the two sample tests. Preferably in model development, we can have two sample tests as well, but it depends on how much population and number of tests we have. Then we have clustering sampling. Yeah, so this is a type of cluster sampling. For example, we have provided two clusters in that sample. in that sample from that population, for example, or we have 2 strata sampling from that population. So whenever you are increasing the value of samples and the number of samples, you're getting much more realistic values in understanding proper things within for the population. One more thing which is important, that's called chi-square test for independence. This is tests whether 2 categorical variables are independent or not. So we had we were previously understanding that and about independent events and not independent events. Right now, we have to understand these categorical variables or within a data set. They are independent or not independent. So that's called for that. We have to conduct a chi-square test. The formula is very simple. So observed frequencies of this variable, categorical variable, in expected frequencies are playing a key role. So you have to find the summation of observed minus expected ones, that you have expected frequencies for that specific categorical variable, square of it divided by expected frequencies, sum of all these ones, and that would be x square. That would be the chi-square test for independence. For example, we have data 50 to 30 and another list 20 40. This is the contingency table, for example. Now we want to perform a chi-square test, and this is the formula for chi-square test. Look, chi to contingency, and just put the data. This is contingency table, and then for that you can, if p-value is, for example, less than 0.05. Why this is 0.05? I really want you to understand why this is all the time explaining. This is where 0.05 is coming. Look, this is 95%, yeah? This is 5% remained. 2.5% here, 2.5% here. These tails. So p-value is actually in these areas, yeah? It means so 95% of data is here, for example. And even if less than this one, it means less than this 5%, it means it's not even located in this curve. It means it's not located in this curve. So that's you have to reject it. So 2.5% here, 2.5% here. So 5% will be, and that will be 95%. This is how the p-value is getting that 0.05 here. So if the p-value is less than that, then reject the null hypothesis. Variables are dependent. If p-value is larger than 0.05, then you fail to reject the null hypothesis. Variables are independent. So for this data, we have conducted a contingency table. We conducted a chi-squared test, and it says p-value is 0.001. So it is less than 0.05. It means the variables are dependent. So these variables are dependent to each other. Now coming to the another chapter. This will be our next module, regression, and I hope we will be going toward the regression next week. Our module of statistics and probability is actually concluded today. However, this is a very basics of probability and statistics. But this is what you need at least, at least, for analyzing a data set and making some conclusions from that data set. If any questions, please ask me. I think, and true negative are the terms used for the type 1 and type 2 errors in classification model training. You're absolutely right, Omid. This is actually and the same thing that you mentioned. Which type of sampling is the best? Which type of sampling is the best? It depends on which question that you're analyzing, for example, and no one can tell you which one is the best. This is why This is why humans are required to decide whenever they're analyzing the data sets and deciding something. You have to decide. Ihsan Faizi, I hope I give you the already the actual example of world hypothesis testing. Yeah, so this bakery was one of that. So I just give you that example. Ashley, please, you have a question on the assignment. I will be sending it on WhatsApp. Okay. Good. So our lesson is concluded. Thank you for your attention and thank you for your participation. Any questions, I'm at your disposal, please. خب سوال اگه دارین سوال کنین. راجب Ashley, if you have question, please ask me. Omid?
Yes, sir. I will be asking it on the WhatsApp. I already sent a message about it.
Okay.
Yeah, sir. Thank
yeah.
you for the nice presentation.
I think it was
I
nice.
want to ask regarding the assignment, anything for this week.
And دیگران کجا حل کرده بودین که assignment نمیخواین. So from the last assignments that we have given, I think the very less number of people have done it. I really don't know why. Even for a very simple one, which was just uploading something to GitHub profile, so no one was doing that.
By the way,
I know that yes, I know that you're doing it, and thank you for that. But that majority of students, they're not just doing it, and I understand maybe that some people they don't have interested, but still, at least we from FemStech point of view, we're trying our best to be and follow our mission. It doesn't affect our enthusiasm. Yeah, so this week ما فکر نکنم که we will be having any assignments. خب فکر نکنم کدام assignment فعلا داشته باشیم. راجع به probability assignment های probability و regression کل زیر بخش model development machine learning باز میاریم که باز همش با هم چیز ربط دارن با یکی دیگه. من منتظر بودم که اگر assignment از یه هفته پورا خلاص میشد یه هفته آینده یک چی می داشتیم کمپیتیشن کاگل لیکن نمیفهم دیگه خوب رقمندی کم است به هر حال good نصرت الله that you have done the homework. دسامبر اشلی گفته که باید چی باشه assignment free باشه خاطر یک سال نوشم می باشه. به هر حال سوال اگر دیگه نیست شما رو بلا میسپارم. خداحافظ شما.